Hello one and all, and welcome to the Math Magic Show. So in this one, what we're going to do is study this relationship, dp over dy equals dq over dx, for a particular vector field, and this is in the context of conservative vector fields. What we're going to do is understand how dp dy and dq dx, how these values of the derivatives actually change the shape of the field. The goal is not to simply find dp dy, dq dx, a lot of videos on that, but how they actually act to change the field, to give our field, a vector field, a curl. So let's take a look at what I mean here. First of all, let me go back to the beginning, and our field will look like this. F like this, with an arrow above it, will be equal, and it's a function of position, so that's why you put x and y, so it changes as you change your x and y coordinates. So as you measure it at different points, you will get a different reading for the field. So here I'm going to have the following. For the x component, I'm going to have y, and for the y component, I'm going to have negative x. I've just chosen this field because it will give us a really nice kind of curling effect that we want to see. So that means the following: since this is often called P and this is often called Q, then dP over dy, when that is equal to dQ over dx, then the field is said to be conservative. Well, now in our particular case, take a look. dP over dy, that's in differentiating the y right here. This derivative of P is just positive 1. And then dq over dx, that's just differentiating the y component of the field, which is negative x. So when I differentiate that, it's negative 1. So that means as you travel, for example, around the plane and you measure the field in different points, as you go from point A to B, for example, the field will change in different ways. And then that is what introduces a curl to the field. That's what the derivatives mean. But let's actually visualize that more fully. So to accomplish that, what I'm going to do is throw a unit circle in here. Let me draw that in here as follows. So for example, we have to be somewhat careful with this process. That looks like that. We have to throw in the usual x and y axes so everything can be neatly labeled. So now I'm going to draw my y-axis. I need to zoom out so I can fit everything just so. So it's going to roughly look like this. If I go all the way across, let's also throw in the x-axis, again cutting right through the center to the best of our ability. So roughly it looks like this. Good. What we're going to do now is just measure the field at a couple different points. So first I'm going to focus on the high point on the unit circle, meaning this point right here. You very likely know that the coordinates at that point are, so this is 0, 1 rather, I meant to say. When you plug those values into the field will be basically an arrow that points to the right. And I know that because if this is my x and y, then look what happens. When I plug it into the field, I'm evaluating the field. At this point 0, 1, so I will have, remember this is x and this is y, but the field says that the x component is equal to y, not x. Let's be clear. So this is going to be 1 here. And the y component is equal to negative x, so that's 0. I'm deliberately going to shrink that a little bit. So it's going to look like this, just so I can visualize the whole thing. It pretty much will look like an arrow going this way. So that's the field at the point 0, 1. It's got an x component, as you can see here, of 1, and a y component of 0. And then let's call this point A, so we can organize our work. What we want to do now is investigate what happens to the field when we apply these equations. dp dy equals 1, and then dq over dx equals negative 1. They have to mean something. That's in some fashion that we can visualize. There's nothing abstract in math. Once you've done it enough, long enough, and you've thought about it hard enough, you realize that pretty much anything is subject to visualization. Well, unless it's like you know, in 4 dimensions. But at these basic, relatively basic levels, it's possible to visualize things. So what I mean by that is the following. Imagine that we traverse the circle to a different point. So I have to be very clear now. I'm going to say this. I'm going to count. Let's say 1, 2, 3, 4. Okay, so I've divided my vertical axis here into some pieces, and I'm doing that because I can keep track of things. And imagine that we want the field at this location, root 2 over 2 and root 2 over 2. That's from the unit circle, so I got it being 45 degrees. So I have to look carefully here, make sure everything is just so. So when I do that, I have a feeling it's about here. So imagine what I want then is to understand what happens to the field when I go from A to B. That's the objective. And roughly approximating, say that the x-coordinate over here is the root of 2 over 2. And then say, for the sake of simplicity, that the y-coordinate is also root of 2 over 2. Okay? Approximation. Now, there's a lot of stuff written. How do you incorporate all of this? So you may want to do is this. Imagine I want to know the x component at b using this information. So what I would do is I would take the x component at a, which is equal, as you can see there, to 1. Now I would add to it the rate of change as the y changes. Now think about that for a second, right? When you go from a to b, this says dp dy, that's the rate of change of p with respect to y. In other words, as you're going down this way along the y-axis, like that. So I would say that that's equal to now the original value of 1, which is this quantity right here. Let me emphasize that, perhaps. And then I'm going to multiply by dp dy, which is 1. And then I'm going to multiply by the change in the y. Over here, since the x-coordinate at point B is the root of 2 over 2, that's about 0.7, which means that the change in the y is this quantity here. See, that's about 0.3. I'm really rough here. It's about 0.3. So what I would do then is back here I would say that it's the x component at a plus the rate of change, which is 1, multiplied by the change in the delta y, that's 0.3. But be careful, because as you can see when you go from a to b, that's actually a negative value, not a positive value, correct? Because it's really going straight down, so it's negative 0.3. Delta y is negative. So I'm going to multiply this way, and then again, just rough approximations, and this is just about 0.7. That would be the x component of the field at b. So what is this telling us? This is already telling us something very important, that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, say 12 boxes, roughly speaking, represent a value of 1. Then this is 0.7 of 12 boxes. That would represent how the x component of the field has changed. So if I find this value, in other words, if the original from a to the right was about a 1 unit, then 0.7 in this context would be the following. We just multiply, so it's 0.7 times 12, that's going to give me about 8.4 boxes. That would be the new component. So in other words, let's count it off, roughly. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, and 8.4 is about here. That's the new component. So clearly there's a difference between these components, and that difference is affected by the fact that we moved from A to B. And specifically, you see the rate of change, which is positive 1 right here. That has a big role to play here, because you multiply the rate of change with respect to y by the change in y, and then you add it back to the original, so that gives a value of about 0.7. So the next question would be, what happens to, for example, the vertical component? So on the original over here, as you can see, the vertical component is 0. Just to remind you, that's this component right here. That's 0. How will it change? Well, we should also now remember that the x-coordinate at b is the root of 2 over 2, and that's a positive quantity. That's just a straight mark there. Roughly speaking, when you work this out, this is about equal to, say, 0.7. That's how the x changes when you go from a to b. Just that portion right here. Look, this is just the change in the x right here. 0.7. So then, to find the new vertical component, what I'm going to do is take the original component, which is 0 right here, and I'm going to act as follows. I'm going to say 0 plus the rate of change, that is dq dx, that's negative 1, and then you multiply that by the change in x, which is about 0.7, roughly speaking. So that looks like that. You work this out, that's about negative 0.7. That's pretty good. That tells you that it's the same number of boxes, but just going straight down, that's all. We can draw that by drawing from the tip of the horizontal component, so let's do that next. So I'm going to just change colors here, and I'm going to count about the same number of boxes down. So it's going to be about, let's see, 1, 2, 3, 4, 5, 6, 7, 8, and then 8.5, so that's roughly that. And then the field itself, well, that would be represented by, for example, an arrow that goes like this. So that would be the field, the green arrow, but it has these components that have clearly changed. And they have changed according to dp dy and dq dx. And notice the following, that because they're not equal, that is dp dy is 1 and then dq dx is negative 1, as you go from a to b, something happens, which is the following, that the x component at a is bigger than the x component at b. So in other words, this here is shorter than it is over here. So that's shrinking as you go from a to b. The x component shrinks. On the other hand, the y component at a has a value of 0, so you can't even visualize it. But by the time you get to B, it clearly has extended. So as you go from A to B, what you imagine is the x component shrinks, but the y component grows straight down. That is what introduces the curl to the field. That is what makes it begin to turn, that unbalance in dp, dy, and dq, dx. Please leave a like and subscribe, and I'll see you in another video.